All right, so today what we're going to talk about is simple harmonic motion. So, what is simple harmonic motion? Well, harmonics, if you're into choir or band or anything like that, a harmonic is basically something where you have some kind of a repetition, right? Something where it's kind of like gotten to a stable pattern, okay? Simple because these aren't too complicated. It can get a lot worse, okay, but we're not going to go there. And motion because everything we're going to talk about as with all physics is motion, okay? So, what do we call this? Simple harmonic motion, we care about simple harmonic oscillators. And an oscillator is just something that goes back and forth at a regular pace or a regular rate. Okay, so you guys have done one oscillator already with rotational motion. So if we got this line right here, okay, so what happens if we spin the wheel? Well, it goes back around and stops right where it started, right? So this would also be a simple harmonic oscillator. A wheel simply going around has a regular period, a regular timing to this thing. So it's going around and around and around at the same rate, unless something is slowing it down or speeding it up. That's what we have to deal with rotational motion. But simple harmonic motion is slightly easier because it's everything kind of going at a simple same rate. Okay, so what we need to do is look at a couple of kinds of simple harmonic oscillators. And in physics, the two things they love more than anything else, wheels. I mean, we love wheels, right? Okay, but the wheel we've already dealt with rotational motion. So the other thing we like to deal with oscillators are pendulums. There you go, and springs. We've already dealt with springs before. Remember Hooke's law? When we talked about potential energy of a spring? Well, we can use that to derive this formula right here. And we will later on. If you want to watch that video, please do. Okay, I'm only going to require it from AP Calculus Physics, but everybody else, you need to know how to functionally use these two formulas for finding the amount of time. And this capital T is weird. This capital T means period. Okay, so it means the amount of time it takes to go one full cycle. So for this wheel, the period for this wheel is the amount of time it takes for that mark to get back to its starting point. So 1 period, 2 periods, 3 periods, so on and so forth. All right? So 1 period, you'll notice 2 pi keeps coming into this equation all the time because that period, okay, the period is that 2 pi, 1 full circle, or 1 full cycle, maybe even better, 1 full cycle over this omega. When we were talking about that, well, the speed, the angular speed that this thing had, or angular velocity, 2 pi, right, it would be 1 full circle. Okay, so the amount of time it takes for that omega to make 1 full circle. Now this omega for simple harmonic oscillators, it can be the same, but it is generally different, and it is always a different quantity. Sometimes you can have that old omega, angular velocity, in a formula with this new omega, and they're two different things, and it's kind of confusing, but don't worry about it because you won't really have to go into it very much, okay? So thinking about it with the wheel, you can think about how fast the wheel was going, right, has everything to do with how long it's going to take for it to go through 1 full cycle, okay, which is our 2 pi radians. So our new term for that omega, instead of thinking about the speed now, I want you to think about repetitions, okay? How often does it actually go through 1 full repetition? Okay, it could be going around in a circle, it could be going up and down once. If it's a pendulum, it's going to swing from side to side, right? Once it goes from there and back to the starting point, that would be 1 period or 1 full cycle, and that would be our angular frequency, even though it doesn't go all the way around in a circle, okay? So, A is amplitude, and this is a different thing, okay? So when we talked about the wheel was just the wheel. The wheel went around, and that was it, right? Period was the period. The angular speed was the angular speed or angular velocity, right? And that was basically it, okay? But now we're going to deal with some new things. So pendulums and springs can do different things than a wheel can. Surprise, right? Okay, so if I have, let's start out with springs. If I have a spring, well, if I pull it down this far, it'll want to come back up to where it was, and then it'll fall back down and go back up and fall back down and go back up, passing some midpoint, right? The relaxed length of the spring. So it's going to have a period also, and that period, instead of going around like the circle did, it's going to be, the period for this thing is going to be once up and back to the start. So if I take and let this go, the point I let it go from, right, it's going to want to pass by some midpoint. So some point maybe right over there, about this relaxed length of the spring, so call it there. Okay? So in fact, let me go ahead and put the relaxed length of the spring as even as I can with the top of the board. Okay, so if I let this and I pull this down, it's going to have a period in which it passes that relaxed length point right here at the top of the board. Okay? So if I do that, I pull it down and I go up, above and down below, up, above and down below, and the amount of time it takes to go from up and back, right, one full up and back is the period. Okay? So for a pendulum, it's slightly different. Its period is going to have to do with, here's a pendulum for you, okay? So let's put some kind of another marker here, maybe the T for the pendulum here, okay? So its period is going to be when it passes that point again, that bottom point, okay? Or really for a pendulum, it can be pretty much any point along its swing. As long as it gets back to that point, you've got your period, okay? And I'm going to talk about it as the center point because it'll always pass the center point. It may not always get back up to the high point on the side, but it'll always pass that center point. Okay, so here's our center point right at the T. So if I let it go, pull it back, 1, 2, 3, 4, 5, 6. So those would be 6 periods, right? The period for the pendulum is when it comes back to where it started. Or once it passes here, again, you can start here. Once it gets to the midpoint, it comes all the way there and then back, that would be 1 period. Going past this point in the same direction. A lot of times, it's easier to look at it at the maximum, right? Because even if it doesn't get back to the exact same point, it gets to the highest point it can get to, right? So from there, 1, 2, 3, 4 back up to the max, 5 back up to the max. Each one of those is your period for the pendulum. So you can see that with this, I could take and stretch this thing back farther, couldn't I? Rather than the wheel just goes around, and it can only go around, right, with however long or wide the wheel is, right, whatever the radius of the wheel is. But with a pendulum, I could put this high point, sorry, looking backwards in here. So if I put the high point there, right, that's going to be where it goes to. But I could take and stretch it back even farther, couldn't I? So that high point could be higher. And that is what we're going to call the amplitude, okay? So basically, if this is 0 when it crosses T, how high up above 0 you get is your amplitude. So your amplitude is how high up or far away you are, okay? So my amplitude here is higher if I let it go. See, it gets to about the same height on both sides, right? So the amplitude is higher if I let it go from up here. My amplitude is lower if I let it go from down there. It only swings a small distance. Here the amplitude is much larger distance that it goes through, and so that's the amplitude. It's basically the height that it gets to or the distance away from it. What about a spring? Well, spring can work in basically the same way, right? Let me again put this relaxed length so it's at the top of the board here, okay? So if I take and I pull it down just a little bit, that's going to be my amplitude. My amplitude is going to be how far off it is from that original point. So you can see it's going the same distance on either side of this thing, and then eventually it's done. If I stretch it farther, what happens? Well, it'll go up higher, and it'll go down lower, and it'll eventually kind of come to a stop again also. But in the meantime, it will go to a higher height when I stretch it to a lower look. See that? So that amplitude is the difference away from that starting point. So with a spring, your amplitude is basically how far you stretch it. With a pendulum, your amplitude is basically how far you pull it over. Okay? So, getting to a point here. I want to talk about the terms inside of this. Okay? So we know what amplitude is. It's basically height away from your starting point, distance away from your starting point. T is your time. It is a time. It is a special time. It is your period, right? The amount of time it takes to come back to the starting point. Okay? T, the other way of looking at it is your angular frequency and 2 pi radians, 1 full circle. Okay? So we've got all this covered. Time it takes to go through 2 pi radians with your angular frequency is your period, okay? And the period for a spring and a pendulum are very reliable things. They're great things to use to make a clock, okay? So the first reliable clock they made was actually with a pendulum. And you can see why, because the only thing that goes into how long it takes to go through one swing, well, 2 pi is a circle, right, or a cycle here. When I talk about a cycle, let me show you what I mean. We're not actually going through a circular motion anymore. We're just going back and forth. So if we plot its position, right, its amplitude essentially over time, if this is 0, and this is going to be our amplitude, and this is going to be time over here, if we plot our amplitude, well, first off, for anything, we're going to have to stretch it out either up or down, right, positive or negative position. And then we let it go, and it will have this kind of a motion to it. So when we talk about 2 pi here, weirdly enough, we're not talking about a circle, but 2 pi will be the amount of time it takes to come back to the original starting point, okay? So that peak in this case, or the trough, if they start with a trough, negative position, okay? So this right here on a graph would be 2 pi. And it's weird because it looks like a line here. Here it is linear, right? Here it's some kind of an angular thing. It's no longer a circle, and yet we can still describe it in circular terms, which is kind of cool. So when we talk about a spring, the period has to do with how long it takes to get from that high point or low point back to that same point, okay? So 2 pi, full cycle, okay? And the other things that matter, the only 2 other things that matter are K, if you remember that, remember back to Hooke's law, K was our spring constant. So it's basically how stretchy your spring is. Is it kind of loosey-goosey? Or is it maybe a little less loosey-goosey, right? A little bit tighter. Takes a little bit more force to pull it down, right? A stiffer spring has a higher K value. A looser spring has a lower K value, okay? So the stretchiness of the spring and the mass that is hanging from the spring. So I don't have any masses really on here to speak of. I have a slight little ring on, well, I don't have a ring on that one anymore. Oh, there it is, okay. I have a clip on this one. Okay, so here's my clip. I have a very small mass on here. So it turns out I cannot change the K value for this spring unless I do something weird to it, which I'm not going to, okay? I'm not going to break the slinky. So if I'm not going to change my K, the only thing that will determine how long it takes to go through one full cycle for a spring to get it back to its starting point, once up and down and back, right? The only thing that will depend on, if I cannot change my K value for this spring, is the mass I hang from the spring. So let's prove it, okay? So, and let's think about it before we prove it. Mass. If mass is the only thing that matters, if I increase my mass is on top. Okay, so if I increase my mass, that number gets larger. So regardless of all the other functions that are happening here, right? If my mass increases, that means my timing has to increase because it's a number on top. Number on top gets larger, my overall value gets larger, okay? If I decrease my mass, my time has to be less. So it takes less time with less mass, okay? So let's do that. I have just this tiny little clip on there, and let's go ahead, and again, I'll get the relaxed length of, or not. All right, let me get this. So the relaxed length, I'm gonna put up at the top of the board so you can easily mark it, okay? So, and again, it's already want to go on its own here, right? So there we go. Starting point is there with the relaxed length. It has a mass of just this tiny little clip on it, which you can probably barely even see. I'm going to let it go and watch how long it takes for one period, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See how regular that is? But also, you can see how fast it went, right? So if I want to increase the time, I should increase my mass. So let's do that now. Let me find my other prop here. Here we go. Big old flashlight with a bunch of big batteries in it. Let's see if it'll actually even work on this, and hopefully I don't break my son's slinky board. So let's see here. Okay, here we go. So now it's just gonna slip off. All right, you know, I will just clip it on like this, and maybe that'll help. And I did slightly change my K value. I'm cheating just a tiny little bit there. Not much. No, that's not gonna work. How about this? Yet another thing. How about I use a pen? Oh, it was too heavy. Okay, so we'll use a pen instead. So I will clip the pen on here. All right. Eventually, here we go. Okay, that works a little better. Okay, so this definitely weighs more than that little clippy thing I had before, right? So let's get the relaxed length. And come on, stop, pen. You don't have to do it, pen. All right. So there we go. Okay, so it stopped about at the top of the board there. So now more mass. More mass should mean a longer time. So I'm going to stretch it out and let it go. And look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Took a lot longer. If I take the pen off, no weight at all. All right? It's just the mass of the spring itself. Okay, if I let that go, pull it down to about the same distance, okay, same amplitude, so you can see that's not the thing that's messing with us. All right, we let it go, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very regular still, but a lot faster. Okay, so you can see the only thing I'm changing on this is just the mass. You can see that it's changed the periodicity. What if I change my K value? Well, I said I can't really do that with spring. I can break the spring. I can do some things to it. Shorten the spring up. That'll actually take care of it. But I can also get a different spring. This one's got a lot higher of a K value. It's a lot more, takes a lot more to stretch it. So if I let that one go, okay, I got a little tiny clippy thing on this, okay? And if I let that hang here, come on, thing, you don't want to do this? Okay, so put it even with the top of the board, stretch it down to about the same amplitude I gave the last one, and, well, it hit too hard, so it actually damped itself pretty quickly. So if I let this go from here, okay, pull it down a little bit, start out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Really fast. So if this is a high value, a high number on the bottom means that your overall number goes down. Because if the large number is on the bottom, you end up with a smaller number overall, right? Well, if I want to increase the time, again, I should be able to increase the mass. So let's see if that still works for a different spring. All right, so here we go. Larger mass on there. So now I'll put it up here. Well, nope, I won't. I'll put it on the ground, apparently. Okay, so I'll put it up here, get it stopped, make it even with the edge of the board here, okay? That's pretty good right there. So now I'm going to pull it down and let it go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fast still, certainly faster than our last spring, but a lot slower than when it had basically no mass at all. What about a pendulum? Okay, so let's take a look at this. Pendulum, the period is dependent again on the full cycle, right? The full cycle that you go through, from where you start to where you end. Sorry. But the pendulum is from where you start until you get back to where you started. That's your full cycle, okay? And it has to do with the length of the string. And it also has to do with gravity. Now here's the thing. Can I change that? Not right now. Not where I'm at. Not unless I want to build a rocket and go to the moon or Jupiter or something like that, which I do not have the resources to do that. I'm a teacher. Okay, so the only thing I change is L. I can't change gravity. Okay, so let me get my pendulum, which is over here, and let's try that out. Okay, so I'm going to put this as the center point. Okay, and we'll come back to here. So if I let it go from here, let's check this out. Let's see if the amplitude matters. If I let it go from here, let's count. Oop. Let's try that one more time. Okay, start up from here. Or I can actually try and get this ready here. Okay, so third time lucky here. Okay, so here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very regular. Okay. What if I increase the amplitude? What about that? Will that make a difference? It seems like it should, doesn't it? Well, let's see. Okay, let's see when it gets back to the highest point. Try not to hit myself in the face. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No difference whatsoever, even though you increase your amplitude. And here's a cool thing of why. Gravity. Gravity's always pulling you down. If you let it go from here, it has less time to get to here, so it gets to a lower velocity. It gets a lower velocity, so gravity only takes a little bit of time to slow it down over here, right? So it's going slower overall. So for the same amount of time, right, you have a lower velocity, and gravity takes less time to work on you because you're going slower. What if you're going up from here? You're going at a higher speed. So gravity is going to take a little bit longer to stop you on this side, but you're going to blaze through the whole time that you're there, okay? So let's go. Let's check it out, all right? So it's going faster overall. I'll give it a little bit of a bump there. It's going faster overall, but the amount of time it takes for it to go through here, right? It takes the same amount of time to stop it there. It's just going faster overall. And so that means that it takes less time to go through one full swing. So actually the amplitude, how far back you pull it, has nothing to do with how long it takes for this thing to swing. All right? What about mass? Mass is not in here at all. Maybe it matters. let's check it out. Okay, you saw about how fast this thing was going on its own. So, it's shutting down on me here. I know this is probably awkward to see, but I want to make sure it's not going to close my computer on me. Okay, so there we go. Sorry about that, guys. All right, so I can put a big old mass on this thing. It's not going to hurt anything. So if I take this, let's try it again. Okay, pull it back to here and let it go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. No change in the timing at all. Mass has nothing to do with it. What about the length? That is the thing we can change. What if I take this, let it go one more time. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What if I shorten up the length? Let's count to 10 now. This is quite a bit smaller, right? This is about half the length, okay? So if I make the thing about half the length, what do you think the time should do? Well, square root of it, right? So if it's 1/2, it should be about 1/4, okay? So let's check it out. Does it in fact go 4 times as fast? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It does. You guys can check it out with your video. You can check out the time and actually see the time value of that swing. So, kind of cool. Basics for simple harmonic motion. This is it, okay? So with a spring, the only thing that matters, okay, for an individual spring, the thing you can't change is your K. For a pendulum, the thing you can't change is gravity. Notice how those are both on the bottom, inside of the square, okay? Inside of the square root. The thing you can change goes on top. With a spring, I can attach more mass easily, right? With a pendulum, I can easily change the length of the string. Those are the things that really we're going to mess with to determine our period for the swing or for the oscillation of the spring, okay, for our oscillation. So the thing you can basically change on top, the thing you really can't or can't easily change on the bottom, okay? That's it. That's simple harmonic motion. When you get into it, we're going to plug it in, time, angular frequency, or sorry, the radians for a full cycle, right? Full cycle, start to finish, back to the same point, okay? Period, full cycle, length, gravity for a pendulum, mass, and spring constant for a spring. That's it.